8th grade's 8.1.2 lesson in CPM, and it's titled, How Can I Describe the Growth? So it says compound interest, and I put simple versus compound interest because we're going to deal with both of those today. So far, we've studied simple interest, which only pays interest on the amount invested. It might be used for informal loan agreements made between parents and children or between like friends. However, banks and other financial institutions calculate interest in a different way. They commonly use compound interest, and we'll learn more about that type in this lesson. So in the last lesson, we learned how simple interest increases a bank balance. That growth can be seen in a table and in a graph. We also saw that in another situation where prices grow by 50% each time they increase, the amount added is not constant. So we saw like those graphs that were non-linear. So a linear, remember linear means a straight line. And the non-linear, if it's not straight, it looks something like this. It could look something like that if something's increasing. So we're looking with non-linear growth today. Okay, so 8:13. Miss Hartley won $20,000 in the lottery. For her. She decided to spend half of it right away and invest the other half of the money for her retirement. So the interest rate on the account Miss Hartley chose is 5%. So she chose 5% interest. She calculated that after 10 years, based on simple interest, her account balance should be $15,000. However, the banker told her that after 10 years, the account balance would be $16,289, so it was different. A financial advisor explained to her that the bank is paying her compound interest. That means the bank is calculating the interest each year on the total of the principal amount and any interest she's earned so far, rather than just on the $10,000. So if Miss Hartley leaves the money in the account for 30 years, her $10,000 will grow to more than $40,000. So it shows you two tables, and it wants you to look at both of them. There's one for simple interest and one for compound interest. And her advisor made these tables for her to look at. So I'm going to scroll down so I can see it. So I don't think I'm going to write out the tables just for sake of time. Time. But part A for this problem says, explain how you see the interest growing in the simple interest table. So if you're looking at the simple interest table, it's in your book or on the screen. It looks like I'm looking at the account balance column, and I'm looking, it goes from 10,000 to 12,500 to 15,000 to 17,500. So I'm noticing there's a pattern, a constant pattern each time. And I subtracted 12,500 from 10,000 to get the pattern. And the pattern ended up being, it grew by $2,500 every 5 years, because the years are in the first column. So every 5 years, she will earn $2,500 of interest. So that's part A. Part B is the compound interest table, and it says explain how the interest grows in that table. So I'm looking at compound interest. Hold on, I gotta grab my stuff. So I'm looking at compound interest, and I'm trying to see if there's a pattern in the second column for account balance, and I'm not seeing a constant pattern because it's going from like 10,000 to 12,763. Then from 12,763, it's going to 16,289. So it looks like it's changing differently every single month. It's still increasing, but it's increasing at a higher amount every single time. So I put the interest is growing by different amounts every 5 years. And the amount between every 5 years is always more than the last one. So it's growing more and more and more and more every single year. There's no constant rate there. So then it says after 30 years, and it shows in the table, how does the simple interest balance compare to the balance in the compound interest table? So I'm going to look at 30, and in the simple interest, it says after 30 years, simple interest will earn her $25,000, and compound will earn her $43,219. So here's simple interest, and here's compound interest. So if you want to really, I kind of did a general, simple interest is almost $20,000 less than 43,000, but you could also calculate that out by just subtracting 43,219 and 25,000 to get the actual difference. But I said it's about a $20,000 difference between the two interests. And that is 813. So now we'll move to 814, and this one does have a resource page with a graph on it that I'm going to try and draw very roughly on the whiteboard, and you can do the same on your paper. Unless you can print it out, then that's even better. Oops. 814. Okay, so I'm going to read this. Compound interest is calculated on all of the money in an account at specific points in time. Each time interest is calculated is just based on both the principal amount, and the principal amount is the total amount deposited at the beginning, and any interest that was earned before. This is similar to how the price of the baseball card grew in problem 8-3. So in the previous lesson, the baseball card problem, it was very similar to that. Because in that situation, each price increase was based on what the seller paid, not on what the card originally cost. And there were all those exchanges, and they were all different. So it says, for this problem, Mariana's grandfather invested $500 for her college tuition in a savings account when she was born. The account pays 5% compound interest every year. I'm going to open up the resource page, but it wants us for part A to fill in the middle column. If you open up the resource page or you open up the e-tool, it'll have a middle column, and I believe it's the balance. Yep. It wants you to fill in the middle table, or middle column of that table. And I'm glad I went through this before filming, because I noticed an error on CPM's part in this table. Because if you'll notice, if you're looking at the table in your book, maybe it's different, maybe it's right in your book and maybe it's just wrong on the internet, but it goes from 0, 1, and it skips 2 years, and it goes right to 3, 4, 5, 6. And I was like, did they do that intentionally? I don't think so, because I started doing all my calculations and it was all messed up when I looked at the answers. It was always like 1 off because they put 3 instead of the number 2 for time there. So we're going to do it the right way. So here's our table, time, balance, and we're going to do 0, 1, 2, 3, 4, 5, 6. And I'm going to look at the correct. It's all messed up. Yeah. Okay. We're going to fill it in, and it shows you in the book $500 here to start the account. Then it goes to $525. Then it goes to $551 and 25 cents. And I know that says 3 in your book. That should say 2. It's a typo. Okay, so this, and then it shows this. Oh, it has a dot. I'm just going to put multiply. It's easier for me to look at. Okay, so each time it's multiplying by 1.05, and you might be wondering where that 1.05 comes from. And I wondered that too. And then I figured, I was like, oh, okay. So 100%, it's going to times 100% of this plus that 5% interest that the account has as its interest rate. So 5% as a decimal, if you want to make a decimal or a decimal out of a percent, move it twice to the left. And since this is a single digit, you got to add a 0 in front of it. So 0.05, wow. 0.05 is our decimal. You have to put the 1 in front because you have to account for the entire 100% is 500. 100% of 500 is 500, and you have to, when you're compound interesting things, you have to add 100% of this as well as the interest rate of the account. That's why it says 1.05, because that's 100% plus 5%, 105%. And as a decimal, it's 1.05. Okay, so that's why it's doing that. If you calculate the rest of the table, here's what I got. 578.81, and all I'm doing is multiplying this previous number by 1.05 every single time to get the next number. So if I want to get the next one, I multiply by 1.05, this one by that, I get 607.80. Do it one more time, actually do it 2 more times. Then it's going to be 638.14, and this is the one I didn't have, but I'm going to do it real time because CPM messed up on that. So I'm going to times this by 1.05, 638.14 times 1.05, 670 and about maybe, I'm not even going to round that up, $670. So that's the middle column, and it wants you to graph it. Oh no, complete the middle column. Yeah, so we completed the middle column, and it asked us how do we find the new balance each year. We find the new balance by multiplying the previous balance by 1.05 or 105%. Okay. I think the next part wants us to graph it. Let's see. Oh, it wants us to fill in the table. It wants us to fill in the rest of the table. I'm going to go to my resource page. Unfortunately, I did not leave enough room for the rest of the table, so I'm going to have to erase some stuff. Yeah, I'm just going to have to erase it. Okay, so for part B, I'm going to make a 3-column table. I'm going to try and do it quickly. Time, balance, total interest. Oh. Times 0, 1, 2, 3, 4, 5, 6. I'm not going to fill in the middle column because, actually, you know what? I have to. 500, 525, 551.25. Feel free to fast forward this. 607.80, 638.14, and 670. All right. Now it wants us to fill in the 3rd column. It gives us, I'm on the resource page 2, and it gives us the first 3. So it goes 0, 25, 51.25. Okay, so it wants us to fill in the rest. It wants us to fill in how much how much interest has been earned so far total off of this balance. So I actually did the really hard way, which was like, I think I don't know how I did that, but now I'm just realizing as I'm doing this that there's a completely easier way to do it. So if you want to find the total interest earned on the $500 from this amount, just subtract this amount and that amount. That's what I'm noticing. So 578.81 minus 500 is just 78.81. This one, 607.80 minus 500 is 107.80. 638.14 minus 500 is 138.14. And this last one is 170. Yep, that's 500 plus 170 is 670. So that's our third column. And now, it wants us to say how we know that or how we did that. And all we did was to find total subtract subtract the balance from the principal. And when I say principal, I mean the first deposit. Okay, that's always the principal. The first deposit. So you're going to find your balance, whatever balance you want to find. You take that balance, subtract it from the principal to get your total interest earned. Okay. Now it wants us to make the graph. So let's, yeah, I'm going to erase it all. I just don't have enough room. I'm going to sketch a graph, and I'm going to model it after the graph. Okay, and the graph is just dealing with the total interest earned. It's not dealing with the balance. So I'm going to make graph 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is the time in years. So that's time. We start at 1, 2, 3, 4, 5, 6. And then this is the total interest, the Y, total interest earned. And I went by tens. Yeah, let's go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. I know I don't have enough. That's okay. Okay, now I'm going to graph. So I'm going to look at my table that I've made. Okay, so here's my table. And I'm going to look at the time. The time is my x-axis. So after 0 years, there was a $500 balance with a total of 0 interest. So 0, 0 is where you start at the interest, because there's no interest yet. Okay, the next one is over 1 and then up 25, because that's where the first interest has been counted in. Then for 2, over 2 up to 51.25. I'm just looking at the table that we made. For year 3, it was 78.81 right here. For year 4, for year 4 it was 107.80, about right there. And then for year 6, it was 138.14, so it's going to be up here somewhere. And then for year 6, it was 170. Eek. So I'm going to put it somewhere up here, somewhere right there. So you'll notice it kind of, whoop, that should have been straighter there. That's our graph. At least the graph that I tried to do. So you'll see that it's not going to be perfect, obviously. So that was the first part of part C. No, it wasn't. Yes, it was. What patterns do we see? So what patterns do we see in the graph and what patterns do we see in the table? So from what I see on the graph, I notice it's not a straight line. It does curve slightly. Okay, so it's going to be hard to draw a straight line there. It is a curve, slight curve up. So that was what I said was the pattern on the graph, and in the table, the total interest. Oh, I keep thinking we're on that one problem. Yeah, so the interest, if we have the table here and it says 0 with the interest of 25, and then the interest of 50, what was it? 51.25, 2 was 78.81, and I subtracted that from that, and it was like 26.25. This was not 26.25. Sorry, this is not right. This is 1, 2, 3. There we go. So it was not going at a constant rate, which is my point. So it was not going at a constant rate every time. It was always a different amount added each time. And that's kind of the gist of part C, to know that it's not going up at a constant rate. Therefore, the graph curves a little bit. All right, let's move on from that one. We spent a lot of time on that one. 8:15 says she is curious about how much money will be in her account when she is 18 and graduates from high school. She went back to the table that she'd created. I'm going to erase all this. She went back to the table, and as she looked at the numbers in the first two columns, years and balance, she noticed a pattern that she thought she could rewrite into a shortcut. I'm going to quickly do this because it's a very important part of the lesson. 0, 1, 2, 3, 4. Her balance was 500 to start, and it was 525, and then she has an equal sign that says 500 times 1.05. Then she has 551.25, which she wrote 500 times 1.05 in parentheses times 1.05. Then she went down to 3. I guess I didn't need 4, which is 578.81. And this time she put 500 times 1.05 times 1.05 in parentheses times 1.05. Saying that a lot. Okay. So she's looking at it. Well, let's look at this. It says, as she works down the table to fill it in, what changes in her calculations? So if you study the table, if we're looking at it, I noticed that she was always multiplying a 1.05 every single time and kept the last one that she multiplied. So I also saw a pattern that related it to the time, which was nice. I was like, oh, okay, for every year, you multiply by that many 1.05s. So after 1 year, you multiply by one of those. After 2 years, you multiply by 2 of those. 3 years, you multiply 3 1.5s to the already 500 every single time. So I don't know if I want to write that in words. Yeah, because I said it. So you guys get it if I said it. So the time in years is the amount of 1.05s being multiplied to the balance every single time. Part B says, in her calculation, for 2 years, what does 500 times 1.05 represent? What is 500 times 1.05 equal to? So 500 times 1.05 is the balance after year 1. That's what that represents. And it's 525, I believe. Yeah, 525. So then part C says, how could you rewrite her balance at the end of any year in terms of the principal 500? In words, generally is the pattern. Okay, so this is where you could say, after 18 years, you multiply 500 times 1.05 18 times. But the 1.05 is the 18 times, not the 500 18 times. So you do 500, and then in your calculator you do 5 times 1.05 times 1.05 times 0.105, 18 of those. And there's actually a way we can make that easier to write down. And some of you might already know what it would look like written down in a new way. So it says part D, to describe how you would find the balance after 18 years without first finding the balance at 17 years. So instead of having to go through all of them down to 17 and then get 18, it wants us to use this streamlined example. And I'll show you what it looks like in the simpler way. So this would be 500 times 1.05 with the little 18 up and to the right of 1.05 called an exponent. So this reads 500 times 1.05 to the 18th power. And that's what we're getting into in the last problem here, 816. So it says it can be written in symbols as an exponent. So here's our exponent. And you've probably seen those before in math. But the exponent, for example, 4 times 4 times 4 times 4 times 4 can be rewritten as, I kind of want to erase stuff, 4 times 4 times 4 times 4 times 4 is actually, it could be written as 4 with this little 5 up there, and that means 4 to the raised to the 5th power. So this does not mean 4 times 5, because lots of us make that mistake. This means 4 times 4 times 4 times 4 times 4, not 4 times 5. So, I skipped this answer. So if you plug, there's actually an exponent feature on most calculators, and you can, so you would type in 500 times, and then you would put 1.05, the little exponent. It's usually like a little caret, or it'll be like, it'll say like x to the y. That's what my phone calculator said. So you type that in, and then you type in the number 18 to get the calculation. So the actual value of this after 18 years is $1,203.30. That's how much she would have after 18 years. Okay. Last part of 816, or of this lesson, is 816, and it's not too in-depth or time-consuming. It's a quick problem dealing with exponents. So 816 is, write the numbers you multiplied in part D as an expression using the exponent. So that's what we did, or what I showed you, 500 times 1.05 to the 18th power. That's part A. Part B says, write an expression to represent this situation. A comic book is purchased for $6. It is resold 7 times, and each time it is resold, the seller charges 15% more than he or she paid for it. So I'm going to treat this like I did this last problem. So the principal, the comic book was purchased, it was $6. So I'm going to use that as my principal. And it resold 7 times with an interest of 15%, or reselling 15% more than 6. So we need to make 15% our rate, because this is always going to be the rate right here. So 15 is 0.15 in decimal form. I'm going to put parentheses just to break it up a little. And then it says it was resold 7 times. That gives us our exponent. Okay, so that means 0.15 to the 7th power times 6, because it was resold 7 times. There were 7 exchanges. Okay, that was a lot of information. That was 30 minutes and 25 seconds of information. And it is time to go. Bye-bye.